Okay, folks, so I lied on the email. We're going to actually do a one thing. Where is the other one? Uh, where is the... Okay. So limit of a function. What's the condition for a limit of a function to be true? I'm going to write that down, folks, because we don't have time. And I'm getting old. Soon I'll be dead. So then, folks, okay, this thing exists. Everybody focus now. You are, everybody's focused. This is the condition for limit. A limit of a function exists, that is, L exists if we have a situation in the domain that all the nearby x's that are near C, that's the center of our, so here's our picture. Here's our C. All the points near, all the x points in the domain near C, x's. I did, yes, good. Thank you, thank you. And I haven't put up the other two, so I'm going to do that, the Monday and the, okay. So here we go. So this is our center point, a point of interest. So I'm trying to do this. I'm going to put this condition on my graph. So this condition says that all the nearby x's, there are x's over here too. Is this x near C? We only think of it if it's near, if it is within epsilon distance of C. How do we represent that? By an open interval here. You guys can see that. So if now is this x near C? Yes, because it is within epsilon distance of C. Have I got this condition down perfectly? What else is this thing saying? That every x that I've plotted here gets mapped, is defined for the function. Every x over here is defined for the function because if I stick any of these x's, I'll find a function value. Okay, so here we go. All right, and then this goes up here. Is this picture correct? Now I'm 59. Medical age. Well, what is this part saying? This part is saying that the difference between x and C better be greater than 0. C is the center point because this is the limit of a function at C usually, right? Okay, so C is the point of interest. We want to know as the function values go from the left towards this point here and from the right towards this point, does this function approach some number? So folks, how do we put this condition in? We can't put it here. In other words, this is saying that x can never have the value of C. This is what it's saying. It was x cannot equal C. In other words, we don't care what the value of x is at C, as we only care about the values of x's near C. Yes, Sophia. So I'm gonna get there. Yes, no, I'm gonna that whole stuff I'm gonna upload it and you can watch it, and then we could also do it again. Because I'm going to maybe, I don't know how much time, I'm gonna get into the differentiation business very soon. But For you, I'm going to stick in a hole right here. There you go. There's a hole. What does this say? I'm going to do it in red. Anybody? Chris, you watching this show here? We have a graph of function f. And at C, the function is defined or undefined? Very good. For every other x in this little open interval, every other x has a function value, except for that. But there is a number here, right? The limit. So the limit does not have to equal the function's value, which is what we did. The reverse was for the continuous. It better be the same as the limit. Okay, all right. And then if this is the case, then what we have is nearby all the points, all the function values nearby. Okay. How do we say that these x values that are nearby C give us function values that also are nearby L? This is what this is saying. All the fx values are near L because all the fx values are within epsilon distance of L. Here's our L. Do this in blue. How do we say that? What is missing here? On this, on the, very good. Sophia just said it. Is that right, folks? Are we good? Yes? All right, next. I gotta move on. If this is true, which we have illustrated, is this true? Yes. What about this guy here? Is this fx near L? No, because it isn't within, we are concerned only. So if this is the case and all the fx's map from this open interval to this second open interval, then L exists. Okay? Now, so this is the definition of limit of a function at some point C. Now I'm going to say a function is continuous at C. And of course, I would have to add what other things? There's a delta, and then there's an epsilon, all of that business, that verbiage that I'm not putting there. So I'm just going to go straight to the condition. If oh, I'm going to rewrite this. Not too close to the picture here. Okay, folks, this is the definition of a function that's continuous at C. And this condition has to be, looks like exactly like that, right? They're pretty close. What's the difference? The difference is over here, we didn't care if the function was defined at C or not. Over here, we want it to be defined at C. We don't want a hole because this function is not continuous. Because over here, you have to lift your pen, then put it back on, or marker. Okay, so in other words, this section here is missing. We want the difference of x minus C to be, because this condition is missing, this is a possibility now. We want this to be true because when we take derivatives of continuous functions, which have their left and their right limits are same. Okay, and then in other words, we want this situation where the functional value equals the limit value. That's the definition of, because what's the other definition of continuity? at a point. You guys remember that? You can either write it like that, or you write it limit of a function as x goes to c equals the value of the function at c, or a, as we were doing last time. This thing can be expanded to look like this. This thing looks very much like, just to see here. So this is the definition of the limit. It doesn't tell us this situation here. But the way to differentiate this as a definition, a limit of a function, and this is, if you notice this guy on that, that's the only difference as far as notation goes. Okay, so now I'm going to take my graph for a limit of a function and fix it. How do I fix it? What little, everything else is perfect. All the x's near c, yes, I've got that down. Within epsilon delta distance, yes. These are the nearby points near c that I'm concerned about. I'm worrying about whether they're defined or not. And they are. They give us all these fx's. And when you see this right there, this is not undefined. This is the, so what's the fix here? Move the pola in the Ayatollah. This is from the 1980s. Yeah, very good, Jake. Make a hola in the Ayatollah. You guys don't remember that. No, when you were demonizing the Iranians back in the 90s. Huh? I know, shit. You guys missed out on all the other shit. Okay, here we go. So now the function is defined at C. And therefore, in other words, they're almost identical with barely little differences. Okay, so in other words, the same kind of notation. What does this say? If you show me a domain, and all I'm interested is in all the points near C, and that's how you represent that. And all of these x's map to fx values, and they better be close to this one, because we're interested in how the function moves towards this guy right here. Okay, I'm gonna now erase all this, and let's do slightly more complicated stuff. This is pretty complicated too. If you missed the classes, I'm gonna put up the videos maybe tonight. Also, I'm gonna grade your stuff, which is basically A or A minus. So don't get an A minus. That means I was angry on the exam. It's like, fuck this, A minus. So it's a new grading system. It takes very little time. Yeah. If you have not done in your exam one, please just write something up and email it to me. Put your name, say, I love this assignment, and email it to me. All right. Because this class is about me, not you guys. It should be quite apparent by now. And my video legacy, the YouTube. Shit, this thing is not erasing. My left hand is not working. It's only 55 years old. Yeah, well, it's getting shaped from my 58-year-old hand. Arm. Okay. All right. Yo, go, Kamla. Okay, sorry. Now, let's move on to some pictures. So I'm going to start with some physics, unfortunately. So we have a road, and there's a car. Or should I put a bike? I'll put a bike here. The bike, well, okay, but this is the bike's initial position. Skateboard, okay. 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 This is a strange looking skateboard. It's not working out. He's going to have nightmares. So we could put a horse here. Anyway, so we have a, let's just say, a motorbike. No, a bike. Okay, it's a buggy. It's a buggy. There's some seats. I am not. I used to be able to draw quite well. It's almost 3D. Okay. There's some teeth in. So this is our Jeep. This is the initial position. Position. You guys know this word? Position. Position. There you go. I'll keep that. It's funny. Oh, thank you. It's also what happens is I'm using the same board and then there's more stuff and it just fucking dies. All right. And this is where the car becomes a truck and stops. No, it's a sedan. Okay, BYD, the Chinese car. Yeah. Okay. So, all right. So it went from this position to that position. Okay. At this point, the time was, we checked the time and it said T1. And then it stopped because the engine broke down at T2. This could be 10 seconds. It went towards the right. We have a direction here. And it ended up on the final X position. So this would be in meters, let's say. This would be in seconds. All right. And then somebody says, give me the average velocity. So, well, first we want to draw. Let's say it was going like that. So the T's would be here, T1, T2, and then each T1s correspond to so this T1, the car was at X1 position, and at that's bad. And then at X2, the car meters here was at this final position. So this is XF, final position, initial position. Okay. This is our something here. So what's the average velocity? It's called rise over run. So we need to do, let's do run first. T2 minus T1 is our run. This is the time it took. This is time. And then final position minus initial position. Now, why are we doing this? Because we are doing it. Now, what happens is, thank you. In mathematics, what happens? We don't use the time thing here. And we go, we have an X here. So this becomes X1. And maybe we could, well, we're getting rid of the X final and initial. And over here, what happens? This is where the function values go, right? Is everybody done with checking your emails? Come on. Or is it text messaging going on? Serious. Just kidding. Am I angry? Do I see angry? I'm watching everybody. Umeed is getting an A minus. Okay. Sorry, Umeed. I have decided. Oh. So what happens here is F's go around here and we replace this. This is what you're going to run into in math. You guys, have you transitioned from physics to math now? Okay, so this is what average velocity, which doesn't make any sense. Maybe it's speed. Because we're using the word velocity because we were going towards the right side here. Now that we have done this, let's move on. And how much time do we have? Oh, thank God. Okay. God bless. So where are we going today in the class? Though the email said we will be doing something else. We're going towards the definition of the derivative. That's where we want to go. So uh, maybe we should just jump into that. We say, I don't know who the we is. This is Bartle and Sherbert definition. Sherbert. And its definition 6.111. And it says, we say that a real number L is the derivative. Now my handwriting is going really bad. Yeah. You jinxed me. And it's also, it's too far up. I'm going to try this again. We say in English, we say that, what are we saying, folks? That we have a real number, L. As soon as I put L, what are you thinking in your head? Limit. The derivative is the limit of the difference quotient and the, we're on the derivatives today. Yes, I know, because I was going to do the other stuff and I'm like, nah. Okay, so L is the derivative of f at c. Now, let's just make a picture quickly just for the hell of it. So here is c, and the number L is the derivative of f at c. So we are thinking about this guy here, right? Is this the L we are thinking about? And the answer is no, ji, no, in Urdu. No, ji. Where our L now is, folks, this tangent line. As in L is the slope of this line. What's the slope of a line? Let's do this. X1, X2, Fx1, and what's the slope of this line that's going up like this? Salop, run, rise over run. So it could be, I mean, just in the terms of the formula. Yes. Yes, this is the slope. Okay, how about if I did this? Excuse me. What about this line? What's the slope of this line? Let's see, here we go. Well, we take 2 points because this is the formula of the slope is you need 2 points. And derivative means at a point. So what we have is this situation. We go, well, I'm going to put a secant line, and then I'm going to make the secant line comes towards our point of interest. If this becomes our C. So all the x's are going to be, actually make this better. Sorry. Here we go. No. Of course, I could just use PowerPoints, but that would suck. No, and then terrible for you guys. Yes, exactly. Okay, here we go. Here's our graph. And we want to find what the slope of this line is, as in, what is this value? So what kind of line is this that goes through 2 points on the graph? This line in blue is called a secant. Secant line. This is a secant line. And what does it give you? It gives you a sense of the slope, right? Which secant line, and what we really want to know is what is the slope of the graph at this point here, at point C. We don't know how to find a slope of at a point, but if you give me 2 points in a graph, I can tell you what the average speed is, which is what the slope is. Or average, what's another way to say that? Average rate. So how do I make this better? This is an approximation of at what rate of change is happening at this point. So how do I make this a better approximation? I get this point closer to this. If these x's are, we get a better approximation of what the slope, the rate of change is at this point if we look at nearby second points, even for the secant line. So it's the same idea. We always look. So here we go. Does this give us, this is our second secant line. Let's call it secant 2. This is one. Which line gives a better approximation of the rate of change right around here? Is this secant line gives you a better sense of what rate of change is happening here, the speed of that car, or this secant line? Number 2, because this straight line looks like, what does it look like right now? It almost resembles the graph. Does this look like the graph? At this point, this line is almost matches the graph, right? What about this one here? I'm now going to put another secant line here. This is almost the right way. So in other words, and then what? In the limit, what we discover is the tangent line. Tangent line is a line that touches the graph at only one point. Secant line is a line that touches the graph at 2 points. The traditional rate of change slope formula requires 2 different points for us to calculate. But in a derivative says that, what is derivative? It's just, what's another word for derivative? Slope. Derivative is a slope of the tangent line. Okay, all right. So I'm going to stop here and keep going. So let's go back to the definition. So we have this line up here. We say that a real number L is the derivative of f at C. I'm going to put an L here, and this is a trick L. Is L the derivative here? And the answer was no, because the RL is actually the slope of this line. How do you find the slope of this line? Well, I'm going to take this guy and stick it here. I'll find 2 points. And what is this point here? X. All right, folks. So then what's the slope of this line? In other words, so can anybody tell me, how did we figure out the slope of this line, that this red line? We use this formula. I just moved it here because we don't know how to find slopes of curves. We don't have that. Okay, all right. Now let's move on. Let's continue with the definition. So the picture is what we get from this line here. The next sentence of the definition goes, if given any epsilon greater than 0, So what is he talking about here? Epsilon would apply to, and then let's see, we have x's here. As we get closer and closer to C, we get, and please stop me whenever this thing is not making sense. So I am going to call, here we go. So this is S1, S2, and then this is S3. Oh, no, this is actually our tangent line right here. So secant line 1, secant line 2 is a better approximation. And if we keep doing this process, we're going to get to a place where this straight line whose slope we can calculate just touches it at one point. So let's go here. Given any epsilon that is greater than 0, what is that saying? Only choose the secant lines that are near. Don't choose S1, and definitely do not choose this guy here. Let's put this. This one is let's call this S0. Is S0 near the tangent line? I'm going to make the tangent line in blue. No, but we can say that these two guys are close to the tangent line. Each one of these, what is S0? And this is, okay, so this point here is f of c. Yes, does that make sense? This point is f of c. What is this point here? Let's call this, this is f of x. What about this point here, f of x? What about this point right here? This is also f of x. So given any epsilon, there exists a delta that is also a positive number whose value depends on this epsilon. So how do I say all the, so I'm going to say what? All the secants are within epsilon distance. This is our second condition, not the first one, because epsilon is always about this side here. All the secants are within epsilon distance of the tangent line, as in slope of the secant line. So the slope of all these secant lines are within epsilon distance of the slope of the tangent line. So we're going to say that S naught is not within the epsilon distance, starting right here. Every and each one of the secant lines that I put right before it stops touching the second point and becomes a tangent line. So what do I write here? Is everybody following? So what we have here is a bunch of secant lines, but only the ones that are very close to the tangent line here, within epsilon distance of the tangent line. And therefore, what's the formula for the slope of a secant line? For in this case, right? All the x's, all the nearby x's minus the center point, the point that we're concerned about, the point at which we want to find the derivative, minus, what are we calling our, we were calling that L, right? So I can stick in our L here. That is the number, the slope of the tangent line. So all the slopes of different secant lines are within epsilon distance of the slope of the tangent line, L. And if you look at this, you think about the limit definition very quickly in your head. Do you? And then we could also, what about the delta? Where does the delta fall? The delta is going to look like this. Delta is and this definition actually has a zero here. So this, if this is true, then, and then this is true, then this function, we can calculate a derivative. That is, we can figure out the slope of the tangent line at this point. Okay, what's another way to state this? So let's do that quickly here. I'm going to have just this. If I had this and then I had f of x minus L, can people see this? If I had this, what's the limit notation for this? This is the definition of a limit of a function, right? So this is going to be limit of fx as x goes to c equals this number here, L. Here we are dealing with, the domain is here, and then our we need to take this description of the derivative and take it closer to the limit expression of this expression and then name that expression as the derivative. You guys are, of course, the STEM people are fine. Okay, so this, we're going to convert this description of the near, how we are only concerned about the nearby secant lines, the slope of the nearby secant lines, to what would be our tangent line. We take this and convert. Okay, what did I just do here? I took this expression that defines when a function has a limit and wrote it like that. I'm going to take this definition and write it in limit notation. So I'm going to say the limit of what? I have to cheat now. The limit of, what's the limit we are thinking about? This whole thing. The limit of secant lines gets you the tangent. In the limit, the secant lines finally approach the tangent line. So we're going to take the limit of this thing, just like we took the limit of what? This guy here, right? This is the first thing, and L was here. It's identical. And then x goes to c, and we still have the same thing. So in other words, I don't know if it's legible, unfortunately. If fx goes here, what is the fx value here? This guy here, right? We got an epsilon, we got an fx, and we have an L. Rather than just an fx, we have this difference quotient. The difference quotient in the limit is the different quotients as all the x's approach c, its distance from L becomes almost zero. So here we go. So I'm going to write this here. And I'm going to do this again on Friday. You guys are welcome to come. Do the whole damn thing. And I'll send out the, okay. And then this should be equal to, what is this guy equal to? L, which comes from here. This thing goes here. Okay. Sophia, come here. Where are you confused? Okay, this is what's happened. Yeah, okay, you can stay there and tell me where to go first. Okay.
I don't know. I don't even know what I don't know.
Okay, so let's start with that. That's a very good place to start. Okay, so what's happened is previously in episode 3, Previously at C, all we cared about was that does C have a limit at point C as the x's go here. Now what we want is we want to know the slope at each point, not the function values. That's what's changed. So in other words, at this point, so what happens is, sorry, I need this picture. I'm going to redraw this. So what's happening is, rather than thinking about where the function tends to, and that ends being the limit, we want to know where the slopes of this graph tend to. So we have this is our first secant line. This is our second secant line, because our interest is eventually at this point. What is the rate of change at this point? But we don't have a formula to figure out a rate of change at one point in the graph. We need 2 points. So the magic comes in where in the limit, all of a second, this thing that has 2 points, its distance, if as long as its distance is within epsilon, it never becomes L, because then we would lose what? We wouldn't have 2 points. So the definition of the slope always stays true. Even in calculus, we are using the definition of average rate of change of slope, which needs 2 points. We never really this never really becomes 0. It's as long as it's within epsilon, we can say we've figured out that this average slope approximates the actual slope at that point. That's the sleight of the hand. Yes, it is, but you cannot stick a tangent line. There's no way. We don't know how to put a tangent line. That's the magical does not actually exist. It's a pretend tangent line. What in the real world we have is secant lines. We do not have tangent lines. So here we go. We got this one works, and then the ones that are nearby, these really approximate the actual slope, which is very, very, very vertical. Because each of these lines gives you the slope of a very good question, actually. This secant line gives you the slope of this whole graph starting from here and here. This secant line gives you the slope from here to here. This secant line gives you that was a very good question. Gives you the slope between here and here. And then this one here gives you the slope right here, which you cannot figure out because you need 2 points to figure out a slope, because we don't have a formula. Okay? So in other words, these things are what's happening to this guy as x goes towards C. Its value gets closer and closer. Does everybody see this? So this, yes. X.
So that's the equation that you.
This here is the. Oh, people, are we done? Okay, so some people, you guys can take off. That's fine. And here. So what is this thing here? For the guys who are the unstem people, keep a look here. What does this say? The derivative of f at C equals the limit of the difference quotient. This thing is the difference quotient. And that is all the slopes. This is all the slopes of the secant lines as x, as these lines get closer and closer to the non-existent. You got that?
Yeah.
So this is what is the derivative? This thing is the derivative. And the notation for that is you put an F and you put an apostrophe there.